colleagues, friends, visitors, welcome to the Department of Materials here. This is a great occasion for us. We're here to celebrate the achievements of a truly outstanding individual. Julian Jones joined our department in 1999, having obtained his first degree in materials from the University of Oxford. And he came here to do his PhD under the supervision of the great Larry Hench. And many of us will be aware that sadly Larry died late last year. Julian's dissertation was on the subject of bioactive glass 3D scaffolds for tissue engineering, and that laid the foundation for his remarkably successful research career that has followed, with a series of prestigious independent fellowships, being appointed to a lectureship in the department in 2007, and then rapidly rising through the ranks. So we're here today for his inaugural lecture, which is entitled Hi-Tec Glass, From Smartphones to Clever Bones. I'll give you Professor Julian Jones.
Thank you very much, everyone. That's a very generous welcome. And so I'd like to also welcome you, and thank you all so much for coming and sharing this occasion with me. It means a lot to me to have people from so many different walks of life over my career that you're all here. So there'll be lots of people who have contributed to my career, to my work, and to this presentation especially. That I can't thank you all, but there will be pictures of people and people's names up as we go through. So if you're wondering why those pictures and names are there, that's why. So what I want to do today is I want to convince you of three things. And that is that glasses are actually high-tech materials. The next thing I want to do is convince you that glasses are the future of medicine. And then also, hopefully by the end, you'll be thinking that materials science is an amazing subject. And it's all about understanding things from the finest scale, materials from the finest scale, right through to their macro properties and how we use them and how we make them better and more useful and help people. So I'm going to do that by using something hopefully you're all familiar with, and that's sweets. And there's my son up there, tucking into one of his favourites, which is candy floss. And my daughter, Sophia, she's a bit more refined. She likes a good bit of chocolate. Also a bit of jelly and marshmallows, which they really can't stand. And then by the end, I'll need your help to identify the final sweet of the day, which I can't find a name for. So to start with, though, I'd like to think about how do we think of glass. Now, I'd like to let you into a little secret, and that is, before I started studying glass, I really didn't think it was high-tech at all. But now I do. And perhaps that's because we don't tend to look at glass, we tend to look through it. But why can we see through it? I wonder how many of you thought about why can I see through my windows? There are two main reasons. Now, of course, we all know light comes from the sun, it comes through. But why does it come through? Two main reasons. One is quantum mechanics. Sounds a bit scary. But what happens is, the light from the sun, the visible light has a certain energy, but not enough energy to get the electrons in the glass excited enough to get active. But UV light, when that hits the glass, it's got enough currency to bump the electrons up to business class, but they use that cash and they don't let it through. So the visible light comes through, UV light doesn't. So glass is already high-tech. Even when it was first invented, back in pre-Roman times, it was already pretty high-tech. Pretty useful to be able to see through glass, but to be protected from UV rays. But the more important reason, and very important for us today, is that glass has this very unique structure. The way the atoms are arranged inside it is kind of random and disorganized. And that's what leads to all the amazing properties and enables us to play with glass and change it. So, glass back in the day, there's a nice pub there from Fleet Street. If you look at the windows, and we're pretty familiar, and even these windows in the Royal School of Mines, they're quite small, they're square. And that wasn't because they thought that was a great design feature. It's because it was difficult to make glass big enough and big enough sheets. So, now that we can make glass in big sheets, thanks to the Pilkington process, we're covering all our new buildings in glass. The new fashion is buildings covered in glass. That's not just because we can make large sheets of glass. It's because the glass sheets are strong enough to go on the building. But, of course, buildings like the Shard, they don't just need strong bits of glass. The keen gardeners amongst you will know about the greenhouse effect. And you can imagine if you're inside the Shard on a warm day, it was like a greenhouse, it wouldn't be very pleasant. So why does it work? Not just because of strong air conditioning, but because the glass has added function. And that is, I'm sure some of you have had reactor-like glasses, but when the light shines on the glass, it'll change color and protect it from some of the heat. But also, the whole building becomes a solar cell. The whole building is, all those glass windows are giving power to the building and powering the air conditioning. Now, I wonder if you can think about what the biggest concern of people covering a building in glass would be. If it was light, you get a clue from our windows. And that is, it's pretty difficult to clean glass on a building the size of the Shard. So why do they use glass? Because the glass is self-cleaning. Now, it doesn't mean lots of R2-D2s pop out the top and abseil down the side of the building. The glass has been changed, as chemistry is understood, so that nothing now sticks to the outside of the building. So it doesn't need cleaning. So what is a glass that enables us to do this? What is this random structure? I wonder how many of you have heard that old adage that glass is really a liquid. Well, it isn't. And Gary, don't get distracted by the liquid in there. It's we'll come to that later. But so it has some tendencies of being a liquid. And that is, a liquid has molecules that are floating around randomly in the solution. But a glass is made of these little pyramidal-like structures, silica bonded structures. And the way they come together is random. And that gives us transparency. It also enables us to play with that structure later. Now, how many of you at home, let's have some participation now. Those of you who've been to my lectures at Imperial will know no one gets away without doing something in a lecture. So let's have a show of hands. Who at home has a lead crystal glass? Well, no, you don't. Because it's not a crystal at all. Because crystal is the opposite of glass. Crystal is an organized structure. Glass is a random structure. Nice to see some Imperial professors putting up their hands there as well. So that's a lead. They call it lead crystal glass, but it's not. It's lead glass. And it's picked because of its lovely, shiny optical properties. But the important thing is it's not a crystal. And because it's this random structure, that enables us to play with it. And I'm sure many of you have got one of these. Any of you, and the branding doesn't necessarily matter. Anyone with a high-end smartphone these days, if you touch the screen, if it feels nice, it's probably glass. And the reason it's glass is because it scratches less badly than the polycarbonate on the older or cheaper phones. And it just feels nice. And now they're able to make the glass thin enough that it can be used for thin phones. But the really clever bit is not just that they're able to make it thin, but they've just changed the structure, the composition slightly. What they've done is they take out some sodium atoms and they pop in some potassium atoms. Now, I know some of you have had salt substitute at home. You switch your sodium for potassium there too. This time it's a bit more clever. Now, what happens, if you imagine you take out the sodium and you're left with a tiny hole, the potassium atom is slightly bigger. And so when they put it in, it squashes the top surface. And that squashing puts stress on the surface. And that makes it harder and more scratch resistant. And the different companies have slightly different ways of doing it. And it's now going to be used on high-end cars as well. Now, I was staring at my phone the other day, as I do quite a lot, get told off by my wife for doing it quite a lot too. And what I noticed was actually in the palm of my hand, I was holding a very important biomaterial. not the phone itself, but the case. The case is made of silicone. Oh, I see my friends at school are perking up at the back there. But chaps, probably not as glamorous as what you're thinking, but the biggest use of silicone in medical devices is this. It's a catheter. And this is actually a hugely ignored part of medical device research. So if anyone's thinking of getting into medical device research, please research catheters, because it's a big problem and a real problem in the NHS. So do that. But the point is, that's silicone. Sounds a bit like silica, but it's a flexible, floppy polymer. Whereas a glass is made of silica, and it's very stiff. So it's about time we got on to medicine. Now, back when as Peter said, I started my PhD in about 1999. And that was just at the time where the field was starting to really get going and evolve. Now, those examples of silica and silicone have something in common apart from the silicon. And that's that if I implanted them into my body, the body would react in a way and isolate them in scar tissue. It would see them as foreign and isolate them in scar tissue and basically try and push them out. In fact, there was a story in the news a couple of years ago where someone was driving on a highway, had an accident, woke up from a coma, the doctors had put him back together, went back to his normal life. 20 years later, he cut himself shaving and a piece of glass popped out of his chin. And that was because a little bit of windshield had gone into his chin. The doctors had missed it, but the body had isolated it in the scar tissue and just pushed it out over time. Some of you may have had splinters and had the same thing. Over time, eventually gets pushed out. So when people were first using materials in medicine as implants, the philosophy was to use materials that had as minimal reaction as possible from the body. So they were thinking the most corrosion-resistant materials, things like stainless steel. But the problem with those inert materials is that the body sees them as foreign and it encapsulates them. And eventually, they do get rejected. And this headline was about this idea of going away from materials that are inert and don't interact with the body towards understanding how materials could interact with the body in a positive way. Start telling cells what to do in a good way. And then perhaps the material will disappear later. So this is a clinical, this is an example of a clinical problem over from St. Mary's, and it's great to have Roger here from the Trauma Centre over from St. Mary's. And this is an X-ray of the knee and below, and it's a traumatic injury. Now, normally, we all know that if bone fractures and you get a hairline defect, then the bone will heal itself, which is great. But if it's too bad a damage, like this one, the clinicians can try and put the pieces back together, but they can't always. So what do? Well, in the tibia, they're likely to get one of these, put it inside your bone is a bit like a tube, and then they'll hammer it in. And they'll hope that that will hold the bone together. If it doesn't, they'll try and find some bone from another part of the body, usually the pelvis. The problem with that is that we don't have much of it to give. And then you've got to heal the bit you're taking away from. Now, there are some synthetic materials that are available commercially that can help, but they don't do the job as much as the clinicians would like them to do. So the idea is that if someone's got a hole in the bone that doesn't repair itself, the idea behind regeneration is that we'll take a material, it will be implanted into that defect, the material will then allow blood to come in, and in that blood will be cells. And those cells are going to do the job we need, the natural process of healing. They'll attach to the sides of the material, and they'll lay down their building blocks. And over time, as the new bone grows, the scaffold goes away, leaving the patient as good as new. Now, one of the main people behind that was my old boss, Larry Hench. He was one of the founders of this field. And the reason for that was that he invented the material called Bioglass. And this glass was the first material that was ever, synthetic material, that was ever found to form a bond with bone. So a pretty remarkable finding. What's probably more remarkable is actually the way it happened. And the way it happened was he was driving, well, he wasn't driving, he was on a bus at a conference, going to a conference dinner. And he ended up sitting next to an army major. And he thought, opportunity here. I can get funding from the US Army. So he said to the army major, I've been working on this amazing radiation-resistant electroceramics. Why don't you fund me? And the colonel said, look, I've just come back from Vietnam. You guys are making so many high-tech developments. Can't you design a material or device that we can implant into the body that won't be rejected? And Larry said that really changed his life. He went back to the lab, wrote a proposal to the army, got funded, did the work. But the next strange thing was that he thought about what he should do, and he thought about making a glass. He thought about needing high calcium in bones, high phosphate. And he put this design together, and he gave it to some surgical colleagues. And the surgeon phoned him up 2 weeks later and said, Dr. Hench, we've got a problem with your material. And Larry said, no, don't worry. This is the first go. I've got lots of other ideas. We can change this. He said, no, that's not the problem. The problem is I can't see what's happened because I can't get it out. It was bonded so tightly to the bone. And this is the first time anything like that had ever been seen before. Now the product, which looks like this, just a powder. It's a powder that clinicians will use. They'll take it out of the packet. They'll mix it with the patient's blood until it clots up a bit, makes a bit like a putty as it clots, and they push it back in, and it regrows the bone. And that product's been used in more than 1 million patients worldwide. Now, unfortunately, as Peter said, a very sad part of the talk is that Larry couldn't be here as he passed away just before Christmas, and he was really, really looking forward to this event. And he's greatly missed. He's obviously missed by me, by his colleagues and friends. And he was a great friend as well as mentor. But here he is, when he first joined Imperial College. And I'm really pleased to say a couple of those people are here today. Here's Maria, down at the front. And if you just about see, being a bit shy at the back, is Dr. Ian Thompson, who's now at King's, and he's up there frowning. Now, you can see Larry was a great supervisor, because on an important work trip to the US, to old Tucson, he got us dressed up as desperados from the old Wild West. There's Ian again. And this is a distinguished professor now at University of Manchester, who some of you will know, Julie Goff. So Larry's got a huge legacy, so I won't go through it all. But of course, he invented Bioglass. But the biggest legacy, I think, is the way he inspired people. He has many companies that have been successful. And then he also managed to write children's books which have inspired kids to get into science, called Boing Boing, the Bionic Cat. So a man really of many, many talents. And he's left a legacy at Imperial. This is Ollie, who's here. There he is. One of my ex-PhD students who got the inaugural Larry Hench Prize for the best PhD student doing biomaterials at Imperial. And that's still running and will continue to do so. But one of the biggest things Larry did when during his 10 years at Imperial was discover why Bioglass works so well. And he did that in collaboration with Dame Julia Polak. And actually, I have to thank both of them, because if it wasn't for them, I wouldn't have met Claudia, my wife, because she worked for Julia, and we met at a Christmas party. So there we go. Anyway, so the thing that they discovered together with Yanis Chinos, a PhD student, was that when they put this glass in with cells, it released ions, calcium ions, silica. And it was those ions that were actually telling cells what to do. That's really important. We'll come back to that later. So it doesn't just bond to bone. It actually releases these ions that tell the bone cells to get active, and tell them to get going and make new bone. And I think that this idea of the ions doing something is what led to guys getting together and coming up with the idea of bioglass in toothpaste. Now, I don't know how many of you use Sensodyne Repair and Protect, but it contains bioglass. It doesn't say so on the box because it might put people off brushing your teeth with glass, although most toothpaste contains silica anyway, which is effectively glass. So it's no different. Anyway, but it contains the active ingredient, bioglass. So why do we have sensitive teeth? Well, it's because we have these. If you have sensitive teeth, it's probably because your enamel is not quite covering all your teeth, and you get some dentin exposed. And in your dentin, you have these little tubules that lead into the pulp cavity where your nerves are. So hot and cold things, painful. Now, some of the original toothpaste for sensitive teeth contain anesthetics. So you brush your teeth, deadens the nerves temporarily, and you feel you're doing okay. The difference in the toothpaste containing the bioglass is that it dissolves, releases calcium and phosphate, and then basically tells mineral to deposit on your teeth. And that is natural mineral, just the same as it's on your enamel and your dentin. So how did I get into this line of work? Well, I was at Oxford doing my research project, and I just got this graph. Doesn't matter what it is. But I just plotted it on the computer, and a lecturer walked up behind me, and she said, you've just got some interesting results? I said, yeah. She said, great. I've got a lecture competition I was supposed to be organizing tonight, and I don't have any entrants. So you're talking. I'm like, really? The winner gets 50 quid. I said, I'm there. And terrible, terrible presentation I gave. But I won, because there was no one else there. And I went on to the Institute of Materials in London for the regional final. And what happened there, Larry heard me talking about wanting to do biomaterials, and he said, come and work for me. I had no idea who he was, and went home and went, oh dear, yeah, that would be quite good. So I came to London and worked with Larry. Before that, I was at Eastbourne College. Here's me, just started. Proud parents on the first day at the big school. And unfortunately, yes, my father also passed away a couple of years ago. Now, he was my first inspiration for doing science because he was a chemistry teacher. And everyone wants to be like their dad at least at some point in their lives. But then I maybe thought maybe that's not such a good idea. But then I was taught chemistry by Roger Edmondson, who's at the back there. So thank you very much, Roger, for coming. And thank you for inspiring me in those chemistry lessons back in the 90s. And it's Roger's enthusiasm that made me carry on a chemistry-style career. And it was for him that I applied to Oxford as well. So thank you, Roger. So I went to Eastbourne, but before Eastbourne, I was brought up in an area that's rather different from South Kensington. And the neighbours are a bit different too. But it was great fun, great childhood in the countryside. So countryside, Eastbourne, Oxford, London. Not sure what's bigger than that, so I guess I'm here. So back to bioglass. So remember, it bonds to bone, but it also tells cells what to do. But Larry's bioglass has all that going for it. The only thing it doesn't have is what clinicians want, is this three-dimensional structure. They want this temporary template that the cells can walk onto. And rather like scaffolding in a building. The cells want to walk on, lay down their blocks, and produce new tissue. So why can't his glass be used for that? Well, the reason is, if you take those glass powders and you fuse them together, they change. They don't stay the glass anymore. They change into the crystal. And I don't like crystal. It's got to stay a glass. It loses some of its properties. So how do we get around that? Well, there's two ways you can make a glass. The traditional way of making window glass is that you melt things together and you pour them out and you freeze the glass. The other way is the sol gel process. Now, the melting process is what we think of as a top-down process. A sol gel process is the opposite. It's bottom-up. And that enabled us to create these foam structures. So on the left, we've got an image of porous bone. On the right, we've got the image of one of these scaffolds made of bioactive glass. Now, what surgeons love is that they look quite similar. So it's a good mimic. Now, this sol gel process, how does it work? Well, it's this bottom-up process. So you start with something that looks very much like water in a beaker. But what's happening there are chemical reactions, and you're creating tiny, tiny particles of silica. And they float around, and then they come together, and they assemble. And you grow the silica network, and it goes from water to a gel, hence sol to gel. And this is a point where I'd like to sort of acknowledge a huge body of work we did with some of my collaborators who are here. So Mark Smith, who you'll hear from later, Bob Newport, and John Hanna. We've spent a lot of time investigating pretty much all you can about this process. It's been great fun. Now, how do we make them porous? How do we make these foams? Well, this is where our first suite comes into the discussion. And that first suite is the famous French meringue. Now, you might be thinking, he's already stretching this a bit far. That doesn't really look like a meringue. But the way we make it is exactly like you make a meringue. And I know that because my mother makes amazing meringues. So, you start off, how do you make a meringue? You start off with your egg whites. You beat it, you foam it with a whisk. And over time, they go from something very liquid and they start to stiffen. And they get holes left in them. And that's exactly what we need to do with this process. We start with the water, we foam it, and we need it to stiffen. And the way this stiffens is through that network growing. So we're growing this silica network, and it's forming together and getting stiff and setting. So the only thing we need to do is get those holes, those pores into it by foaming. Now, what the sol doesn't have, that the eggs have, is the ability to keep those bubbles in there. So what I'd like to do now is introduce to you Pilar Sepulveda, who actually invented this process back in Larry's lab, back in about the year 2000. So Pilar, please come out. Come. And now what she's going to do is demonstrate to you the process. But I know, Pilar, you like a bit of competition. So we're going to bring up my first PhD student from 2005, that's Gaush, and my current PhD student, Hung Kai. Now, Pilar, if you go down the end, that's a smaller lab coat. So if you just put those on. Now, who today has washed their hands with soap? That's a few more than what the students normally require. Now, have you noticed what happens when you wash your hands with soap? Now, when you wash your hands without soap, you still rub your hands. And you may think you're not getting any air into the water. That's not true. You are. So the difference is when you wash with soap and you rub with the soap and you get those bubbles forming, what you're doing is keeping the air in the water. And that soap is stabilizing what's happening. Right, guys. So, unleash your weapons. So what they're doing and I'll explain to you the rules at the same time. Right, so the rules are, you have a foaming tool, you have 100 milliliters of water, everyone's got the same, and you have in your syringe, if you all locate your syringes, you have surfactant. You can decide whether to keep the black thing in place or not. I would recommend keeping it in place. Right, so you've got your syringes. Right, so everyone's syringe in hand? Oh, yeah, have you found the on button? That's a good point. Right, okay. So what I will do is give you 20 seconds to produce the best foam. And what we're looking for is stable foam. So we need it to be expanded up, and then you need to pour it into the molds, just like we would need to do in this process. Okay, are you ready? 20 seconds starting now. Now what they're doing, you see, if you look at the diagram, is they've got the sol. They're doing the vigorous agitation with the help of surfactant. And what they're looking for is getting bubbles to stabilize in the sol. And then when they're happy with it, they will pour it. Right, 20 seconds is up. Pour, pour, pour. Right, so now we will examine the evidence. Very nice, Honkai. Best one you've done. Little bit of spillage there. We need a bit of Mary Berry, don't we? Gauche, or lots of collapse going on there, Gauche, I'm afraid. So the winner is my mentor, Pilar. So we created these foams, and we've got this porous structure which looks like bone. But the important thing is not just the structure, but it tells the cells what to do. So the unique thing about Bioglass, you put human bone cells on the surface, and they will attach, and they will create new bone without adding anything extra. It's the glass telling them what to do. I'm very proud of this picture because I actually did the cell culture back in a long time ago. But Olga did a lot more of the work. And then, so it's very important to test these things biologically. So we go from creating something useful, testing them with cells, and then they have to go in vivo. Now what this shows is a tibia, and this is a top-down X-ray cross-section. The implant goes in this big hole in the tibia. And over time, you can see the bone, this is the healthy bone, the bone grows back through it, and this then degrades. And you can see in this one, in 3D, the scaffold is starting to degrade as the bone is regrowing. And that's the sort of thing we're always looking for. So we've got this glass that's reacting with the body, telling the body what to do. It's got this porous structure that's allowing the bone to grow in. It's degrading once the bone is growing in. So what is it not doing? Well, it's not getting around this problem. That if you used it in a tibia, you still need to put this metal shaft to keep it in place. So we need things that are a bit more flexible. We need things that will take some flexibility. Now, the amazing thing about glass is if you make it thin, it becomes very flexible. And actually, it can be quite strong. Now, this is optical fiber. Those of you with Infinity broadband, other broadbands are available, would be having stuff like this running under the ground. Probably not to your house, so they don't get that far. Almost. So it's flexible. You can use them as endoscopes. You can bend the fibers all around each way. So one of the big problems with the Bioglass and other similar materials is that they don't have that toughness. So we move on from 1999, that headline, to the Daily Express in 2009. Doctors, we can keep you young. Now, could mean anything. But if you look underneath, new body parts will reverse the signs of age. So they're saying in 10 years, 10 years again, there will be organs available off the shelf that clinicians can put into your body and keep you young. So to try and do that, we need this mechanical changes in the glass. So Gausch and colleagues at here and at Nagoya Institute of Technology, where I'm a visiting professor, have been working on this cotton wool process that Gausch devised. So what happens is that you have the sol, still sol gel, sol in the needle, and an electric field basically spins it out to a collector. Now, that is very similar to what Lizzie's doing over here, making candy floss. And the properties of the material are almost identical to candy floss. You can see it spinning out there. Whee! So, what can we use candy floss for? Well, you can use it any way you want the properties of bioglass, but something a bit more flexible. So one option would be a dentist putting it into the bone under the teeth and regenerating the bone in the jaw. But really exciting work coming out of the US from a company called MoSci is they've got a different type of bioglass that they've done this spinning with. And they've been able to regenerate and heal wounds in the feet of diabetic patients where those wounds were never going to heal in any other way. And they were healing them within a matter of weeks. So Karen's over there. Maybe he'd like a bit of candy floss. There's Karen over there. He's ready. So we think that these properties, this flexibility, for some reason, is great for diabetic patients, but we don't know why. We don't know whether it's the structure. We don't know whether it's the ions. So we're hoping to find out. But that's never going to take load. The candy floss, you know what candy floss is like, right? It's never going to take load. So the big mission that we've been working on for the last 10 years is getting flexibility, toughness, strength, all of the above, into a material, but keeping all those amazing properties of the original bioglass. So how do we do that? Well, what we do, we take this bottom-up process. We're creating these networks. But while the silica network is growing, we're introducing the polymer in, and the two things intertwine right at the finest scale, a scale that we can't see, a scale below how much your fingernail grows in an hour. It's that fine. And that's important because that's the only way we're going to get these properties. And the reason we can do that is because the sol gel all happens at room temperature. So you're not going to damage your polymer. Now, that's quite easy to do, as Gausch found. But if you just put the two things together and make a scaffold and drop it into water, the water pushes in and pushes everything apart. And it dissolves just like sugar. So what Gausch and I worked on was this idea of getting the polymer to bond to the bioactive glass bit. And he did that by using this tiny molecule called, which had groups that could react with the polymer on one end and silica groups on the other end that will bond to the silica, the glass. So that when you mix it together, you grow this thing called a co-network. Network of one, network of the other, and they're knitted together. And then, when Gausch drops it into the solution, notice these high-tech degradation studies carried out at the world's number 4 university. And it doesn't degrade. Great. And then Ollie, we saw him in the picture earlier, was able to make these scaffolds from gelatin and silica, and was able to get properties right from that of packaging foam right through to a glass, and you could choose anywhere in between. So that, again, wouldn't be useful for bone being that flexible, but it shows just how far we can go. But what we got really excited about was Francesca's work, where we're finally able to hit it with a hammer. And my coffee cup. So, and so it's really exciting to be able to hit this with a hammer, and it contains glass, but of course it's got the polymer in there as well. And what it shows is that one fractured, one didn't. The one that fractured was stiffer because it had higher silica content. The one that didn't was lower silica content, more polymer. So it shows that we can go anywhere in between glass and packaging foam and get the right properties. And then one we're really excited about is this one. Now this one, we think is going to be great for intervertebral discs. Now you've all heard of slip discs, and there's also degeneration of the cartilage in the disc. So here's my spine. Of course, there's bones that are all stacked up, and in between those bones, there's cartilage, being a cushioning property. And if that cushioning property goes, then what clinicians will try and do is fuse the bones together. And the reason they have to do that is because there is no material currently that can take the place of that disc. So we're hoping we've got it. So this is glass. It's an amorphous material, but it bounces. Now, I've been really looking forward to this. So everyone, eyes on me. Who's a cricketer? He's at the back. Can't reach it. Right, everyone ready? Let's see where it goes. Good. Well, a round of applause for that catch. So yeah, Justin, one of my PhD students, very proud, very proud. Right, so but then really interesting as well was that when Francesca gave me one of these before she got the bouncy one, in a group meeting, I looked at it and I said, "Oh, you're nearly there. It feels almost right." And then went, I'm like, "Oh no, I've broken it." We put it down and got on with the meeting. At the end of the meeting, I said, "Where's that one that's cracked?" And I couldn't find it because the crack had gone. So she's giving that a real good tug. She's cut it in half, put it back together, and it's healed. So this is a material healing itself, let alone the body. And the reason it does that is because of the way the bonding is happening inside. So she's cutting permanent bonds and dynamic bonds. The dynamic bonds come back and grip it back together. But we've got to make these into scaffolds. So this is where our next sweet comes along. Chocolate. Oh, it's gone. So we want to make it into scaffolds. We want to make it into scaffolds. Of course, we could foam it like we did before. But there are several reasons why we go away from foaming and towards 3D printing. One reason is that we can, because 3D printing is a layer-by-layer process, we can choose almost any pore architecture we want. So the clinician could send us a CAT scan, a CT scan, and say, "I need this." We can feed it into the printer and print it. The other reason is the size of those pores can be very important for the application, and we can control that. And the other reason is that if you line up these struts, you can get very good mechanical properties, much stronger than you can with a foam. So that's 3D printing chocolate. Chocolate's actually quite easy to print because you can warm it a bit, it becomes soft, and then as it cools, it gets harder again. But instead, we use the sol gel process where we go from going from the sol again to the gel. So we print the sol, and then it gels as it prints. Now, what we found is that when we get that pore size right, we get really exciting results in terms of what the cells do. Now, this again is cartilage. And cartilage, as many of you know, is a real problem. It doesn't heal itself like bone does. So this is a really important area. Now, what we found when we put cartilage cells onto these 3D printed scaffolds was that the cartilage cells produced a particular type of collagen which is specific to articular cartilage, the cartilage in your joints. And that's really unusual. And as you know, cartilage is an amazing material. It not just acts as a bearing surface, it's also a cushioning material too, something we can't replicate. But if we can grow it in the joint and let the body do the rest, then we've got a chance. Oops. And Amy's also been 3D printing the traditional bioglass. And she can do that by changing the composition so it doesn't crystallize into the ceramic. And what we found with work from Christopher Mitchell, who's also here, is that perhaps the the printed structure works better than the foams in terms of bone ingrowth. Now, I've been telling you about these hybrid materials, the way we're getting these two things knitting together. A big area, but the polymers we've been using so far are ones that are available off the shelf. We buy them from suppliers, and we modify them, and then use them. So we've got a large program of work now where we're deciding, well, we don't need to buy them. What we should be doing is designing them right from the bottom up. So we're designing our own polymers that we can directly bond with silica into the bioactive glass. We're adding in biodegradable linkers. We're doing all sorts of things to the chemistry because we're designing them how we want it rather than going out shopping for the polymers. Right, I said we'd be looking at some jellies and marshmallows. These are Ali's gels, and the fun thing about these gels is that they're very much like cartilage. And they swell. So this is before you add water, then you add water and it swells. And that swelling allows cells to live inside that gel. These are Paul's marshmallows. Now these are for a bit of a wacky application in that they're designed to go up people's noses. And they're designed to be soft enough they can go up the nose. But then you can pull out the mucus or some cells, then analyze those when you pull them out. And that will tell you what's wrong with you, what respiratory condition you have. And that's work going on with guys over in St. Mary's as well. Now, the last thing I want to talk about is going back to this property of the bioglass releasing these things that act a bit like drugs and tell cells what to do. And it's well known that ions do different things. So silver has got famous antibacterial properties. I'm sure you've probably bought socks that say silver technology. And that's because they've got antibacterial properties, at least until you wash them and the silver goes away. And actually, the work with Bioglass was started by Maria Bellantoni in Larry's group. Cobalt has been shown to stimulate blood vessel growth. And Gavin's here, who was doing that work in Molly Stevens' group. And now he's out in UCL carrying on that work. Strontium is great for osteoporosis. The strontium tells the cells that take bone away to stop, but keeps the cells laying down bone active. And Molly's group's doing a lot of work on that. And I'm really excited about lithium, because that's good for your knees. How did they find out? Because people taking lithium drugs for mania, when they had bad knees, their knees got better. Now, a lot of this is based on work that's been taken by pills. But of course, pills go in and they go systemic. You take them into the stomach and they disperse the drugs. So the idea here is that we make tiny, tiny particles. Again, too small to see. And when these particles go into your body, cells take them up. But the cells don't actually notice they've taken it up. So that's ideal for sort of being a Trojan horse and delivering some of those active ions into the cells. So for example, you could load one of these particles with strontium, and it can be taken up into cells and deliver that strontium inside the cell as the particles degrade inside the cell. And these guys have been doing a lot of work on this, and they've even found some particles that seem to kill cancer cells quicker than they kill healthy cells of the same tissue type. So that's really exciting, but that's for another story. So this is an image that Shu took of the particles entering the cells and doing their stuff. So this is really high-end microscopy. So I was saying I needed your help. I need to know what suite to call this. The best I came up with was Tic Tac, but I'm really not happy with that. Other small sweets are available, probably, but I don't know what, otherwise I'd have called it that. So, all that remains for me to do now is to say, hopefully I've convinced you that confectionery is the future of medicine. And perhaps, if we had a headline for tomorrow, if anyone who wrote headlines was here, they might do that in a very aptly named tabloid. And perhaps in 10 years, great things will happen. So the last thing to do is to thank my group members over the years, in addition to those people you've seen. And the group's changed quite a bit over the last few years. And this is the most recent one. And thank you all very much for listening, but also I'd like to, special thanks to, of course, my wife Claudia, my mother Diane, Delia for always helping when I need to go traveling, and family friends for being here, and mentors, Bill Bonfield, thank you very much for your mentorship when I was doing my fellowship. Larry, of course, and all the other collaborators and colleagues and friends that are here. Thank you for listening.
So for those of you that obviously there's many people who won't know me, my name is Mark Smith, and I'm one of the many people that have had the pleasure of working with Julian. And the format, I understand, at Imperial is to make a short reply to the inaugural lecture. First of all, can I congratulate you, Julian, on bringing alive and making very accessible the very wide range of very detailed and complex work that you've done. And I think it was a great way of spending an hour. I certainly, an area I thought I knew a little bit about, I certainly learned a lot in the last hour, so thank you very much for that. It was fantastic. But I want to reflect back, because I've been very lucky to be involved very early on in Julian's career, because here we have myself and Professor Bob Newport, who's in the front row over here, were at the time colleagues at the University of Kent, and we're in a materials department, we feel a little bit outnumbered because we're a couple of physicists who actually had really one interest. You know, you dress it up a bit, but really we had one interest, which was to answer one of the questions that Julian posed at the very start, which is how do you describe the structure of a disordered material like a glass? Bob's a scatterer, both neutrons and X-rays, and on an NMR spectroscopy. And what we'd done is basically combined the data sets from both of those materials to come up with a description of a glassy material. And we were working out what to do with this. It was technically very interesting. What do you do with it? And we realised that Larry Hench was here, who we didn't know, and was doing some very interesting work on bioglass. So around about 2000, Bob and I kind of plucked up the courage to come and have a chat with him because we realised he was an enormous figure in the field, and he granted us an audience. And we had a very nice cup of tea with him in this building, where basically the point that Bob and I made, we should put a grant application in. That was the kind of thrust. And Larry's response was very generous in a way, was a good idea provided you write it. And that's exactly what we did. We did, and he was very, to be fair, he was very supportive of us and helped in the draft. But it was very clear when we started, and it was funded. This story wouldn't have gone very far, I guess, if it wasn't funded. But it was funded. But it was very clear that while Larry was a huge inspiration, he didn't want to get involved in the detail of the project. And so he delegated. That's one of the great skills of leadership, is to delegate. And he effectively delegated to Julian to be the Imperial person on the ground doing the project with Bob and myself, which then started off a period of somewhat over 10 years of doing some of the work that you've heard about. And I'm going to just recount a couple of Julian stories from within that period. Nothing too scandalous. I can tell you the scandalous ones later, actually, in the bar. But no, the first one was because of the expertise that Bob had in using synchrotron X-ray sources, we could do very fast diffraction. And what we wanted to do was follow the reaction of the bioglass with simulated body fluid in real time with X-ray diffraction. And that's a very challenging experiment. It's not only challenging because to collect the data, but you actually have to design a cell which you can put in the beam and inject the simulated body fluid in real time and then take the data. So we did this at the SRF, and Julian used to come along with us to do the experiment. Now, one of the things which he's kind of hinted at is these materials are quite brittle. And the problem with that experiment was you had to cut it very thin to actually get it thin enough for the X-ray beam to diffract off it. And it wasn't that easy, was it? So very late at night, on about the 20th attempt to cut it, as it all kind of fell apart, there was some very colourful language later at night. But we eventually did manage to cut one that was thin enough to do the experiment. And at that time, I was very impressed. Not with the language, I have to say, but actually with the perseverance, because we were on the point of saying, well, we should give up and go home, basically. But Julian kept saying, no, we'll definitely get one. And he absolutely succeeded. And I think that's an indication of his tenacity as a scientist. The other one, which I'm surprised you actually didn't use, was one of the things that we discovered, which in retrospect may be obvious, but I'm still astounded. I don't know whether my colleagues are, but I'm still astounded by this, is when you put it in a simulated body fluid, Julian made the point several times that these ions move all over the place, but they absolutely move at a tremendous, the calcium comes out almost instantaneously from the surface, almost instantaneously. And that work was quite well reported, actually, in the press. And I don't know if you remember what the Daily Mail, it wasn't a headline, that's not, but it was an inside story. But the Daily Mail capture was, scientists absolutely prove a pint of milk a day actually is good for your bones. Because they had, of course, equated the fact that you've got calcium in milk with the fact that we'd shown that the calcium was the key determining factor of how well the bioglass worked. So I think you should, somewhere on your website, have that headline, because I think that's probably what you'll be remembered for, that you proved that milk was good for bones. But there you go. It was a bit dodgy. But nevertheless...
I can tell you why I didn't. It's because the Daily Mail article didn't mention names.
Oh, I see.
So my grandmother wrote as disgusted from East Sussex. But it wasn't his.
It was definitely his fault. That was the point, yeah. But anyway, the serious point is that, of course, underlying... I want to make kind of 3 points. Underlying this, of course, the point you make is that science, although it's a kind of, it's a way of making a living, it's a vocational way, it also is a very social activity. And the fact is that I agree entirely that it was a lot of fun, the work, and Julian was a tremendous collaborator. And I think that one of the things that I think is true, I mean, it was obviously very sad that kind of Larry passed away at the end of last year. But a scientist's legacy are really 2 things. They are the contribution they made to the field in terms of the work they did, and there's no doubt that Larry Hench was a giant. But it's also the people that they encouraged to come into the area, and the fact that Larry encouraged Julian to come into this field, I think, can be no greater testament to Larry Hench. The second thing to say, and I'm going to put a little bit of pressure on you now, actually, Julian, is that I've had the pleasure across my career of working with some very bright people. But I have to put Julian up there with the brightest. And when Bob and I met him for the first time, it was clear almost instantaneously, because he was very young, okay? He was still in his PhD when we met him. Yet he was confident for someone of his age, let's not say overly confident, but was full of ideas and energy and wanted to work. I've had that experience, although I've worked with many very bright people, I've only had that experience once before. It was about 15 years before the time that I met you. That person now has gone on to be a Fellow of the Royal Society and one of the most highly cited chemists in this country. My prediction here tonight is that by the time you finish your career, so don't let me down, that by the time you finish your career tonight, that you will be a Fellow of some learned society, and if the Royal Society don't make you a member, that's their fault. And the second one is you'll be one of the most highly cited material scientists in the country. So it's been a great pleasure, Julian, and I think you've demonstrated tonight. It's a pity that, I don't suppose there are any politicians in the room. It's a pity that there aren't any politicians here, because they would see your lecture today, how you have to go all the way from very fundamental science, understanding, wanting to be curious about things at the fundamental level to be able to make real progress into things that then become products that make a difference to people's lives. So many congratulations on the professorship, many congratulations on the talk tonight, and best of luck in the future. Well done. Well done.